Hmm. So let's start the exercises at the end of section 5.5. So in the first one, we are given a subset E of the real numbers, which has a least upper bound m, that is itself a real number. It means two things. The first is that because we already know what the definition of supremum of a subset of real number is, the fact that this m is real first of all says that the subset is non-empty, so that the supremum is not minus infinity, and the second thing is that the subset has at least one upper bound, a real number which is an upper bound, so that the supremum is not plus infinity either, it is a real number. Now another set minus e has been defined, which is just the set of the negatives of all the elements of E. We have to show that the negative of the supremum of E is the greatest lower bound of this set minus E. That is, minus m is the infimum of minus E. So let's see the solution. So to prove that minus m is the greatest lower bound of minus e, we need to prove two things. First of all, we need to show that minus m is a lower bound of minus e, and the second thing is that we have to show that it is the greatest among all possible lower bounds of minus e. So let's first show that this is a lower bound of minus e. Let minus x belong to minus e, where x belongs to e. This is how a general element in minus e looks like, since m is an upper bound for the set E. M is the least upper bound, that's fine, but after all it's an upper bound. We have x less than or equal to m. Because x is an element of E, so x should be less than or equal to this upper bound m. This implies minus m is less than or equal to minus x. So this arbitrary element minus x from minus e that we chose has to be greater than or equal to minus m. So that just shows that minus m is the lower bound for minus e. Hence, minus m is a lower bound for minus e. We now have to prove that it is the greatest of all the lower bounds. Let L be any lower bound for minus e. Then L is less than or equal to minus x for all x, for all minus x belonging to minus e, but that just is equivalent to saying for all x belonging to e. That is, Okay, so now if we multiply on both sides by minus 1, we would get this. Minus L is greater than or equal to x for all x belonging to E. This shows that minus L is an upper bound for E because it's greater than or equal to every element of E. And hence minus L is greater than or equal to M because M is the least upper bound. M is the smallest among all the upper bounds for E. And this last inequality implies L is less than or equal to minus L. So now note that L was chosen to be any lower bound for minus C. We have proved that L is less than or equal to minus M. So that means minus M is greater than or equal to every lower bound. But at the same time minus M itself is a lower bound for minus C. So that means it's the greatest lower bound. Thus minus M is the greatest lower bound for minus C, that is minus M is the infimum of minus C. So that's what we wanted to show. So this completes the solution. Okay, then exercise 2. So in these exercises we are going to justify the few steps that we used in one of the proofs, namely in that proof which is somewhat tough, which shows that the system of real numbers has the least upper bound property, and those steps were not justified in the actual proof. So those steps are going to be justified in this next few exercises. Now this is one such exercise. Let E be a non-empty subset of R. Okay, let n greater than or equal to 1 be an integer. So n is a positive integer, and let L less than k be integers. It has been written in a somewhat short manner. It just simply means let L and k be integers satisfying this inequality. Suppose that k divided by n, we can divide k by n because n is non-zero, is an upper bound for E. is an upper bound for the set E, but that L by N is not an upper bound for E. Is not an upper bound for E. Okay, without using theorem 559. Show that there exists an integer m satisfying these inequalities, L strictly less than m and m is less than or equal to k, such that m divided by n is an upper bound for E but that m minus 1 divided by n is not an upper bound for E. Okay, and hint is also given, although I don't think we are going to follow the hint. Prove by contradiction. And use induction. It may also help to draw a picture of the situation. This last line of the hint, this second line, is actually a general useful advice in mathematics and in some other subjects also. If you can draw a picture of the given situation, whatever the situation may be, then that helps a lot instead of simply thinking logically. I mean, of course you have to think logically, but instead of, what I wanted to say is that instead of thinking in terms of abstract symbols, if you can draw a picture depicting or representing a given situation in some sense, then that is always better, because if we can see something in front of our eyes, that helps a lot. Okay, so okay, anyway, you have seen the question, the exercise. I wrapped this up. The thing is that we are given two integers, L and K. Note that the exercise does not say whether L and K are positive or negative or zero. That thing has not been, nothing like that has been said about L and K. The only thing is that L is less than K and N is a positive integer. We have to prove that there is an integer m satisfying these inequalities such that m divided by n is an upper bound for the set E, but m minus 1 divided by n is not an upper bound for E. I forgot to mention, the other thing that is given is that L by n is not an upper bound for E, but K by n is an upper bound for E. Okay, so that's what we have to show here. So let us start the solution, and in the solution we are going to use a set and the set is this. Consider the set A, which is the set of all integers I such that I is strictly greater than L and less than or equal to K, and such that I by n is an upper bound for E. So we are considering this set. Say it is the set of all integers I that satisfy these inequalities and such that I by n is an upper bound for the set E. Note that A is non-empty because K belongs to A. Why does K belong to A? Because we are already given that K by n is an upper bound for E, and K definitely satisfies these inequalities because K is less than or equal to K trivially, and it is given that L is less than K. Okay, so in place of I we can take K. Also, A is finite because A is a subset of the set of all integers satisfying these inequalities. It's a subset because here in this set we have only a part of the hypothesis that we need in the set A. So naturally A is a subset of this. That means it just contains all the integers satisfying these inequalities. A additionally, A has to contain all such integers, or A contains all such integers, but additionally they also have to satisfy this condition that I by n should be an upper bound for E, and this set is a finite set. And the latter set is finite. In fact, its cardinality is K minus L, which can of course be proved using the properties of finite sets that we have already seen in a previous chapter. This is k minus L. Okay, so that means A is a non-empty finite set. So it will have a smallest element, it will also have a largest element. We need the smallest element of A here. Let M be the smallest element of A. Okay, so there are two things in this statement. First, M is an element of A, and the second thing is that M is the smallest element of A. So because M is an element of A, M satisfies these inequalities. In place of I, we can put M, and M divided by N will be an upper bound for A. Thus, L is less than M is less than or equal to K, and M by N is an upper bound for E. Upper bound for E. Okay. Also, because M is the smallest, so the smaller integer M minus 1 does not belong to A. So that means M minus 1 does not satisfy both these conditions. That is, either M minus 1 does not satisfy these inequalities, or M minus 1 divided by N is not an upper bound for E. Then either this is not true, or this is not an upper bound for E, or both. That is, neither are these inequalities true, nor is M minus 1 by N an upper bound for E. Now, to complete the solution, we need this part, that this is not an upper bound for E. But what happens if, say, we don't really know whether this is an upper bound for E or not, but these inequalities are not satisfied? Then what happens? Assume that we don't have L less than M minus 1, which is less than or equal to K. Since M minus 1 is strictly less than M, and M already is less than or equal to K, our assumption forces the conclusion that m minus 1 cannot be greater than L. So it has to be less than or equal to L. Okay. Then m minus 1 divided by n is less than or equal to L divided by n. Naturally, since L divided by n is not an upper bound for E, m minus 1 divided by n is also not an upper bound for E, because it's less than or equal to L by n. L by n not being an upper bound for E means there is at least one element in E which exceeds L by n. So automatically that element will also exceed m minus 1 divided by n, proving that this is also not an upper bound for E. So now you see, either this is not true or m minus 1 by n is not an upper bound for E. If these inequalities are not true, then also we are getting the conclusion that m minus 1 by n is not an upper bound for E. So which must be true in any case. So in any case, we have that m minus 1 divided by n is not an upper bound for E. So that completes the solution, because we have shown that m satisfies these inequalities. M by n is an upper bound for E and m minus 1 by n is not an upper bound for E. In the next one, in the next exercise, we have to prove that this m is actually unique. Let E be a non-empty subset of R. So it is the same thing, it will start similarly. And let n greater than or equal to 1, be an integer and let n and m prime be integers with the properties that m by n and m prime divided by n are upper bounds for E. That is, m and m prime are like that m. Both are like that m. But m minus 1 divided by n and m prime minus 1 divided by n are not upper bounds for E. Show that m is equal to n prime. That proves that this m that we have got in the previous exercise, that is unique. This shows that the integer m constructed in exercise 552 is unique. Again a hint. Again, drawing a picture will be helpful. Okay, this time we are going to solve this by the method of contradiction. Suppose m is not equal to m prime. Assume without loss of generality that m is less than m prime. Because we have supposed that they are not equal, so one of them will be less than the other. So we are assuming that m is less than m prime. Okay. Then m is less than or equal to m prime minus 1, because these are integers. So if we subtract 1 from m prime, that will be still greater than or equal to m. At most it will be equal to m, but it cannot be less than m. This is not true in general for real numbers, but for integers this is true. We have already seen this before. This implies m divided by n is less than or equal to m prime minus 1 divided by n. Since m prime minus 1 divided by n is not an upper bound, for E, there exists an element x in E such that m prime minus 1 divided by n is strictly less than x, because if it becomes greater than or equal to every element of E, then it becomes an upper bound for E, which contradicts the hypothesis. So there must be at least one such x. But then m divided by n is also less than x, which contradicts the hypothesis that this is an upper bound for E. So that means our supposition is wrong. So our supposition is wrong, that is, we must have m equal to m prime. Instead of assuming m less than m prime, if you assume m prime less than m, you just have to switch the roles of m and m prime in these arguments, that's all, and you have all the things necessary to carry out that version also in the hypothesis. So this completes the solution and proves that the m we had in the previous exercise, that is actually unique. Then exercise 4, let Q1, Q2, Q3 and so on be a sequence of rational numbers with the property that the absolute difference between Qn and Qn prime is less than or equal to 1 over m whenever m is greater than or equal to 1, this is an integer, that is m is a positive integer, and n and n prime are integers greater than or equal to m. Show that this sequence is a Cauchy sequence. Furthermore, so once you show that this is a Cauchy sequence of rational numbers, it will have a formal limit. Now we can say something about the formal limit. If S is the formal limit of this sequence, Qn n tends to infinity, show that the absolute difference between Qn and S is also just like that, those inequalities less than or equal to 1 by m for every okay, here we don't have general n but m itself, for every integer m greater than or equal to 1, and there is a hint. Use exercise 548. It follows from exercise 544 that the sequence Qn is Cauchy. How exactly it follows from that exercise that this is a Cauchy sequence, that I leave to you, because you have to go back to this exercise and see what we are doing here actually. You will see that this is quite straightforward. You can directly conclude that Q1 is a Cauchy sequence from the result in that exercise. Okay, so that means the first part is done. We have a Cauchy sequence Q1, and that's why we have its formal limit. We now want to show this inequality is true for every positive integer n. So we are definitely going to use this part. A special case. Oh, but before we do anything, let us just first fix this positive integer. Let m greater than or equal to 1 be an integer. Okay. A special case of the hypothesis is this. Which one should we choose, M, and which one should we choose this one, capital M. It's a special case of this hypothesis because in place of this n prime we have chosen capital M itself. Okay, and n small n is varying. This implies if you write these inequalities slightly differently without using absolute value, then they look like this: Qn minus 1 over m is less than or equal to Qn, which is less than or equal to Qm plus 1 over m for every n greater than or equal to m. Okay. So, if we now use the result of exercise 548, you will see that in that exercise we are given that if, say, you have a sequence Qn that is all of whose terms are less than or equal to some real number r, say, or some rational number, whatever it may be, then the formal limit of this sequence is also less than or equal to r, provided of course the given sequence is Cauchy. Here we are dealing with a Cauchy sequence. Since Qn, where n is varying from capital M, not necessarily from 1, this is a Cauchy sequence and is equivalent to the original sequence. Exercise 548 implies if you take the formal limit of this sequence where n is varying from m to infinity, that formal limit will also be greater than or equal to this and less than or equal to this, and that formal limit is nothing but capital S, because these two sequences are equivalent. And that equivalence itself actually tells us in the first place that this is also a Cauchy sequence. So, taking everything into account, we write these inequalities. Thus, now if you write this again using absolute value, then the inequality will look like this. Since m was chosen to be any positive integer, so this is true for every m greater than or equal to 1. So we have shown what we wanted to show. So this completes the solution, and it actually completes this set of exercises. And we are going to end the video here itself. In the next part, we are going to start the next section 5.6, where we will deal with real exponentiation. How we can take say r is a positive real number. Okay, how one can take r to the power x, where x itself is a real number, that we will see. I can't remember exactly whether we are going to define this power where x is real in the next section, or where x is rational in the next section, because there are two parts of exponentiation. Whether this one is the second part or the first part, I don't think we have dealt with real exponentiation yet. We will see what it is in the next part. Okay, so with that, we are going to end things here. So see you in the next part. Until then, it's me, Lucifer, from a mathematical room. Have a nice night.